Weird, I think, personally, to include it in organic chemistry as much more than just a general concept of, hey, we can do this. The reason being is that polymers are such a massive area of research that they really deserve their own course. Okay? And they have their own nomenclature system. It really does kind of suck to introduce it in open. Okay? So lots of different materials. So breaking it down first, we get multiple mers, polymer, okay, or multiple pieces. Okay? So if we look at a single one, then that must be our monomer, or one repeating unit. So if we're going to look at a polymer with that monomer there, what would it look like? Yeah, we just generate a line with a big string of beads attached to it. There we go. We now have our polymer. Okay. What if we had multiple types of monomers? Is that going to change what we see? Okay, say we've got the black circles on there. What happens if I added red boxes? What are the possible polymers we would see now?
Number of combinations.
What do you mean? I don't understand.
You could have a pattern of those in many different.
We could have a variety of patterns, and really there's only two common patterns we can get. Okay, the simplest or the easiest one to recognize would be alternating. Okay, black, red, black, red, black, red, black, red. Okay. The other one, which is what I think you're alluding to, is saying that we have patterns. It goes black, black, red, red, black, black, red, red, or black, 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 red, black, 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 red. Okay, which kind of sounded like a song. The consistency or the ability to get a reaction to run like that, though, we don't have. What are you thinking now? Oh. No, we're going to avoid that. Okay. The ability to get that to work isn't going to happen, because if we had black, 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 what's the problem? Well, the middle black now needs to be consistently the middle black. But if it's still a monomer, it has to be identical to the ones on the outside, which then means it's not its own unit. It would be a new piece. Okay, so then we'd be looking at three types of monomers coming into this. So what ends up happening is that we get what's referred to as our alternating polymer, and I forget the name on it, but we have our alternating pattern. Then we have what's known as a block polymer. Okay? And in the blocks, we'll see runs of all red or all green. Okay? In this case, red versus green. Okay? Or it could just be 2 reds and then 5 greens. They're random kind of patternings of what was the next molecule or the next monomer unit that appeared. Okay? So it's not a consistent patterning, oh, I know it's this one next, I know it's this one next. Because we don't have, at least yet, the control at the atomic, really kind of molecular level at this point, to be able to build a polymer in that fashion. Okay? At least organic chemists can't. Okay? So we get what's known as our copolymer and then the block copolymer. Crosslinking. When we look at our individual monomers, they must have at least 2 binding sites. What if they only had 1 binding site? Can't create a longer structure. I would only end up with what kind of a structure? What was that, Troy? If I only have 1 link in each of those cases, I end up with 2 coming together, and I would have a monomer was 1 piece, polymer was many, we end up with a dimer, okay? Which we've heard of before in the Diels-Alder, in theory that was mentioned when you looked at the Diels-Alder reaction. Diels-Alder reactions have a tendency, or the dienophile has a tendency to make dimers. Okay? So most of our polymer materials, it makes sense to not just make a dimer, because that's pretty useless. And we have at least 2 binding sites. This way we can propagate out, if I want to get really lazy in it, building it outwards. But what happens if I have 3 binding sites? What's that? So what I've got shown up there isn't a chain?
Why is it
I can then, get different chains bonding to each other. Okay? Kind of like a fence, right? We have our runs of metal fence that then crosslink. We end up with crosslink chain fences. This is known as cross-linked polymers. Okay, we're connecting those polymer chains. Okay, is that going to change the property of our polymer? Wow, how?
You can make bigger structures. So you get four.
I don't accept bigger necessarily.
Stronger, more complex.
Potentially bring in a level of complexity. What are you suggesting on stronger?
The more bonded it is, the stronger it becomes, less likely to break.
How do I separate those two polymer chains now?
Cut a lot of strands.
What do you mean cut?
There's a lot more strands.
What am I cutting?
Break.
What am I breaking?
The bonds between.
Chemical bonds. What if I did not have that cross-linking? Now to separate those, what am I breaking? Not necessarily electrostatic, right idea. You're still too specific. What am I breaking? I'm breaking the intermolecular forces. If I cross-link them, I'm breaking chemical bonds. If I don't cross-link them, all I'm breaking are intermolecular forces. Okay? So cross-linked polymers tend to be a lot more difficult to break individual polymers away. Okay? What is that going to do to some of the properties? Okay, well, I might expect less stretchy. Okay? We could also expect it to be much more rigid, potentially brittle. It's now going to hold its shape and not move. Why? Because there's chemical bonds holding them in place. Whereas in the other case, I had intermolecular forces. Those have the potential to give and slide a little bit. So depending on how much cross-linking molecules I put in there, let's just say I put in one, okay? Now those two chains are bonded at that point. If I put in a second one, that's going to progressively change those properties. Kind of make sense? Okay. So here's a fun part. What is the shorthand? So realize when we're looking at our polymers, we're adding a whole bunch of monomers here. Okay? To accurately draw a standard polymer that we're working with, I need probably on the order of 300 to 500 of those little black dots, which there's no way I'm going to draw that. Sorry. Okay? So that's a bit tedious. How can I come up with a shorthand to better represent that? Or more efficiently represent that?
Do little brackets with the number of how many.
Okay, put brackets around it to represent the number of how many. So I have 1, 2, 3, 7. Let's just say it's 700. Like that, right? So now I've got a polymer that has 700 of those individual units within it. Does that get me to that end structure? Does that not get me to a repeating unit that has 700 of those little pieces in it?
It does, but it doesn't tell you like what the ends look like.
True, it doesn't tell you what the end look like, and believe it or not, we don't care about what the ends look like, because in a structure that has 700 individual monomer units, how many ends are there? 2. The overall or the overwhelming aspects that we're going to be concerned about are going to be everything running through the middle, the 700 interactions through the middle. The tail ends typically are going to be pretty irrelevant. Right? Anybody see any other patterns that we could do with this?
Type of, if it was the pattern one, or if it's
No, just within this, I want another shorthand. What do you suggest, Sean? 3, what's 700 divided by 3? I don't know.
230 something.
Let's just say 233. Does this get us to the same final polymer? Yeah. Okay, well, if we get the exact same thing, which of those shorthands is better? Probably the one we have to draw less stuff for. Okay, so the red one's not as good, the purple one's better, so we should just stick with the purple one.
Can we just do
How about we just do that? Yeah, I agree with that. So when we're looking for our polymer shorthand, typically what we're trying to do is draw our brackets around the smallest repeating unit possible. Okay? And propagate from there. Usually, in my perspective at least, and unfortunately, it is not IUPAC, okay, but it does appear to be widely accepted. We're trying to draw it around the individual monomer unit. Okay? So that way we can see where our monomer came from that builds our larger structure. Kind of makes sense? Okay. So then let's test you on that. There's another pattern that I could use here. What is that other pattern? As a hint. Yeah. Does that not also get me the same result? Yes. Why would I pick the red one over the black one? IUPAC. Remember all those nomenclature rules that you've been dealing with? Okay. And those rules came from the international... Yeah, UPAC. System. So somebody came down and said, these are the rules on how we generate our names. Well, polymers are a very similar system. Someone came down and said, this is how we draw a shorthand for polymers. And in that shorthand, where do we start our repeating unit? Do we have a way to start any kind, or do we have a ranking system already established within IUPAC? Yeah. What was that ranking system?
For what? For
Not really. Kahn, Ingold, pre-log rules, which nobody remembers. At least no one of my students would ever remember that.
what?
For establishing RNS, okay, we rank by our highest priority atom. Okay. Sometimes the highest priority atom is very cleanly at the beginning of our monomer, or we could at least draw it that way. Sometimes it's in the middle of the monomer, okay, which would then change how we represent our polymer structure. Okay, so we have to be a little bit careful and aware of that issue, okay, because you won't get tested on that weird notation. Okay, but I'll show it again when we actually run it into a structure. Okay, kind of makes sense. So what we're hoping for is our repeating unit within our polymer systems will contain just the monomer, and we can just copy and paste that monomer out all the way through. Kind of makes sense. So how would we do the next one? Or either one of those next ones. What's that? I'll give you 10 seconds, then I'm giving you the easy one.
The middle one, you want the IUPAC one?
Well, IUPAC we can't officially do, right? Because we don't know which is higher priority yet. So we
you
want...
just want to bracket the red and green one. And then do 700.
Okay. Are you making fun of me?
It's not, you can't see them now.
Oh, you can't see it over this, what you're saying. Okay, I was like, I thought I did a pretty nice job filling that in.
It's totally gone crap on these squares and blocks.
I think if I do that, though, it doesn't look very green. It looks black. Oh, no, that actually looks green. That's actually a really good green. I'm going to stick with that. Okay, sorry. New investigation there. New tools. And then we would say however many times this repeated out for that individual polymer. Okay. Because in theory, these polymers continue on forever. We don't really know, so that would just be our end. That's how we would show it. If we wanted to get really detailed, we could go through and specify the number down here. Sometimes you'll see me just write X, saying it's some unknown number. Who cares? If you want to get really specific, you could specify the number, and we had 1, 2, 3, 4? In this particular case. Make sense?
4 pairs.
Yep. 4 repeating sets. So that if I copied and pasted this structure out 3 more times, I would end up with what was shown. Make sense? So it shows up 4 times. And since you guys got the easy one, I guess I'll give you the hard one. Okay. So in the block copolymer, we don't know how many times it's repeating out through that. Okay. So we'll just say it runs some amount of times. The next one runs some amount of times. And in theory, that notation allows us to say, oh, it's going to continue out either direction some repeating number of times. Okay. And that sets us up. Make sense? Yes?
Would you put how many times, like right next to the Y? So
For your total number of monomers, it probably makes sense to go through and specify that. And that X and Y would really not be saying how many times it repeats, but how many times that monomer showed up in the polymer in sum total. Make sense? Last thing I want to point out, where did I draw the parentheses?
Around the individual.
Around the individual structures. What did I draw the parentheses through?
bonds.
The bonds. Your parentheses will always go through bonds, never through atoms. Okay. Well, within the shapes, it's a little bit weird.
Oh.
Okay. But your parentheses will always go through a bond, never through atoms. Okay? Other questions on that? Okay. So, what is the appropriate shorthand for the following polymers? Spend a couple minutes here, see what you can come up with. We'll take a look at the one that did not have an answer. That's our repeating unit. So if we copied and pasted out, let's color over that in red. Okay. We've got the second repeat. We've got a third repeat. Everybody see that? Okay, so that one works. Okay, that works as an individual unit. Let's take a look at the first one. Okay, there's a repeat, which would then go to, right? Does that look like it works? Everybody happy with that? Okay, remember, when we're trying to identify our repeating unit, though, we typically try to do what? Include every atom within the repeating unit, or within our monomer, sorry. Okay. So that says, to get this polymer, I need how many carbons? 1 carbon. And that 1 carbon will have to act as what? A nucleophile and an electrophile simultaneously. Do we have that happen fairly frequently? No, that's pretty rare. This repeating unit, if we're going to draw the monomer unit, or draw our parentheses a little bit more precisely, should include 2 carbons. Why? If I had 2 carbons, 1 can act as the nucleophile, 1 can act as the electrophile, a little bit cleaner. Both of those repeating units work officially. The one that you picked, Troy, is really what's running in kind of the IUPAC standard. Okay. The secondary kind of common name effectiveness for our polymer is usually shown what's in red. Okay. How about the one that Tyler picked? Why did you say you wanted to change it?
Because I missed the carbon. I would have changed it to where I included the carbon to the left of the nitrogen.
We've got our carbonyl, our carbon, and our nitrogen, which would mean the next thing we look at what is identified in Tyler's repeating unit. We've got the nitrogen, and we have the carbonyl. We're missing the blue carbon in that polymer, or that repeating unit, which means you're right, that doesn't work. Okay. So what we want to do is draw it in such a way that we can include all of those atoms. I would argue that's the best repeating unit. Okay. Why? I'm trying to draw it so I represent, again, the polymer. or our individual monomer, and I'm drawing a line through the bond that connects the individual monomers. What bond am I drawing a line between? Don't tell me the red one.
Amine and a carbonyl.
Which is an amide bond. How would we form an amide bond? Nucleophilic addition and elimination. Oh, you mean the chemistry we just learned? Yes, exactly right. That's how we go through and form that polymer. It's the exact chemistry from this unit. This is why we're bringing in polymers now. To generate that type of polymer, I'm using the chemistry from this section. Okay. The other way that we could potentially circle this would be this fashion. Any ideas why I might not like that pattern?
Because you have a carbon acting as an electrophile.
I have a free hanging carbon, okay, which doesn't really make a lot of sense. In the previous system, I had an electrophile in the carbonyl and I had a nucleophile in the nitrogen. Both of those make sense. If I look at the purple structure, I may have a nucleophile, but then I have an electrophilic, so a positive primary carbon. Ooh, that's not very likely. What have we drawn in that purple parentheses? We've broken the monomer up and only organized it according to the priority of the atoms. Purple is officially your IUPAC nomenclature for polymers. The black one is the one that I would argue is easier to understand and better to follow, because you see the monomer within that repeating unit. Yes.
So if we were making this dough and we wanted to do the purple one, could we just have that be like an SN2?
So
Or you had
if we were making it, the purple one doesn't exist. It doesn't work.
No.
Yeah.
It wouldn't work. Even if you changed it just a little bit to react.
No, not very cleanly at all. Yeah. Okay. Last one. I would argue a couple things. Number one, I'm going to complain about that first parentheses because it looks like it's going through an atom. So ideally we clean that up and it should actually go through the bond. Okay. This does work as a repeating unit. This could theoretically then copy and paste outwards. The issue I'm going to have with this one, the same issue that I had with the one we just looked at. Okay. We're drawing parentheses through a bond that is not easy to make or break. Okay. The better place, in my opinion, is to draw it through the easier to make and break bond, which would be the amide bond. Going through those. Now I can copy and paste out. This helps me to recognize that I have one monomer and a second monomer. This is actually a copolymer. Okay, linking those individual units with each other. Okay. How many of you found it really easy to look at your shorthand within these systems? Oh, fascinating. Nobody found it easy. One of the reasons why it is more challenging is because you don't know how these individual polymers were formed. If you don't know what the monomer potentially looks like, because you don't know how it's going to react, you can't predict your shorthand quite as easily. So maybe it makes sense to look at how we can make these. Okay. There's two primary formations for your primary ways to produce your polymers. You get addition polymers and you get condensation polymers. The condensation polymers you can fully expect to have a higher priority as far as this exam goes, because how do we make our condensation polymers? I believe it's through a nucleophilic addition and elimination. Oh, with carbonyls. Oh, you mean like the exact same material from this unit? Yes, exactly. Okay. Why do we refer to them as condensation? The first condensation polymers that were run produced water. That water, or to get that reaction to go, we had to run it at extremely high temperatures, which means the water boiled and then later condensed, hence being referred to as condensation polymers. Okay? The addition mechanisms can happen in a variety of fashions, though the radical one tends to be kind of one of the more common ones. Why would we do radicals with alkenes as opposed to not radicals? Do we have clean nucleophiles and electrophiles on our alkenes? They can really act as nucleophiles. Can they act as electrophiles? Not really well. Okay? So it's kind of difficult, at least from an educational standpoint, to convince students that our alkenes can go through anything other than a radical mechanism. Okay? Some kind of patterns. We have electron donating groups and electron withdrawing groups as potentials. Okay? So we can see how those can potentially affect our repeating unit outwards. Okay? With that information, when we go backwards, this top one, I remember what Troy had represented was just the carbon. Are either of those mechanisms just a single carbon? No. Which polymer did we make in that first example? Addition or condensation? How do you know it was an addition? There's no, I don't quite accept pi bond. What do we expect to see in a condensation? When we do a nucleophilic addition and elimination, we're doing a nucleophilic addition to a carbonyl, a polar pi bond, and the elimination results in the formation of a polar pi bond, which then means when we run a condensation polymer, what had we better see in the polymer?
Oxygen?
We need a little bit more than that. We need a polar pi bond. When we look at that top example, there are no polar pi bonds, so it's not going to be our addition or our condensation polymer. It's going to go through our standard or our addition type as opposed to condensation. In our addition type, we need to start with an alkene, and an alkene minimally requires 2 carbons, yes. What were the R groups? Hydrogen. Okay. We move to the next slide. Remember, we've got those potential for R groups. Okay, so what was our monomer for that first reaction? We had 2 carbons, and our R groups were hydrogen. That's how we made it. What about this one? And a pi bond. What ends up happening? We just connect, and we lose our pi bonds. Kind of makes sense? See the patterns? Is that a question, Michaela? Which part? Okay. So when we're looking at our shorthand, what we're trying to recognize is first what type of polymer. So this one should be an addition. Are you okay with it being an addition and not a condensation? Okay. We just set it up where our backbone is what did the polymerization. The backbone must be what functional group if it's an addition polymer? Has to be an alkene. So there's my backbone. Is there anything that's not, attached to the backbone? Sorry, not part of the backbone. These things are not part of the backbone. They're attached to it, but they aren't part of it. So those must be attached to my red alkene. Okay? Because I've identified my repeating unit within those parentheses, I now just need to include one of those things. And I now have my repeating unit, or my monomer. If I draw this out as several repeating units, what ends up happening? The pi bond can attack, the pi bond can attack, resulting in the loss of the pi bond, but the formation of that new sigma bond. And I now have the polymer. Does that make a little more sense? Kind of makes sense? We good? Okay. So our addition polymers go through a free radical. Okay, so we almost always add an initiator. Okay, and that initiator usually requires light. What functional group are we starting with in that initiator molecule? What's that? Where's the chemistry happening in that first molecule?
The oxygens.
Between the oxygens. What type of bond do we have when we bond oxygen to oxygen? We have a peroxy bond. Highly unstable bond because oxygens are both electronegative. That causes that structure to cleave open, particularly under light, and we form the two radical molecules. Those radical molecules will then interact with the next highest energy thing. What's the next highest energy thing? The pi bond. And we end up doing a radical reaction with our pi bond, okay, which then moves through a propagation step, because the result of that step is another radical. Start with a radical, end with a radical. That's propagation. That propagation is going to continue until when? What's that? We run out of alkene. We can't do any more propagation. Okay? Or, what else could it potentially do to stop it?
The other equivalent of the peroxide.
If it encounters another radical. Because what happens if that encounters a radical? The radicals quench each other, in which case there's no more radical. So it's not a propagation, it's not an initiation, it's termination. So we have our three primary categories for our reactions, our radical reactions. Our initiation, we start with no radical, we make a radical. Propagation, radical to radical. Termination, radical to no radical. Okay. Our condensation polymers. Okay, what are we starting with? Well, we're starting with a species, a carbonyl, and our carbonyls act as what? Electrophiles. What else do we need? A nucleophile. And if we look at the other end of this molecule, we have a nucleophile. So what can happen? Our nucleophile can attack, form the tetrahedral intermediate. Step 1. Step 2, what happens? We eliminate ROH, and we would have the first part of our nucleophilic addition elimination polymer, or our condensation polymer. That then continues out multiple times over. Let's come back a little bit. What is the likelihood that that polymer will yield in a high, oh geez, sentence structure kind of fell out the floor there. Are we going to get a good yield from this polymer? Why not?
Because the carboxylic acid group will deprotonate, and the oxygen no longer makes a good leading group.
The amine is a decent base. The carboxylic acid is a decent, well, acid. Probably the first thing to happen would be something along these lines, which then means no nucleophile. Do I still have that carbonyl though? So why are you saying no electrophile?
Because it is stabilized heavily by the resonance.
We have resonance stabilization of the electrophile, which then means no electrophile. Okay? So we have to watch out for that acid-base chemistry. So if I did want that polymer, how could I change this to make sure that I get that polymer?
Keep it in acidic.
Protect what, though? If I protect the alcohol, how does that help me? I think I see what you're saying. So if we turn that into, say, an ester, then we don't have an acid. Yeah, that could work. What else could we do? I can accept that. Same idea.
Could you run it under
Safe
acid?
conditions.
Run it, make it an acid chloride. Now I don't have the acid functionality, and I have a much better electrophile. Okay. I heard a couple suggestions on making it under acidic conditions. If it's under acidic conditions, what happens to our nucleophile? I still lose the nucleophile. I may still have the electrophile, but I lose the nucleophile. That gets rid of half my puzzle. So really the only way I can get this one to work is by getting rid of that acid functionality through two possible methods. I can either turn it into the ester, which I had not even considered, so good job. Or we could turn it into the acid chloride. Or test on Monday or Wednesday. It should be Monday, right?
I thought you were asking the 23rd.
It's scheduled for Monday.
Okay.
Smart works due Friday.
I think it makes sense to do it on Monday because I have a feeling you guys really don't want to be here on Wednesday. I'm still going to be here and I will lecture. And if I'm the only one here, I will lecture to an empty room and I will record that lecture.
Thanksgiving service.
So you're not getting Wednesday. That's why I'm bacon.
We could turn it into That's not, doesn't quite work. That's our anhydride. The issue with turning it into the anhydride is that and for that matter, the acid chloride, it's very self-reacting. Okay, so it would polymerize almost instantly.
And because that's an acid, you can't run it under basic conditions.
Yeah, if we ran it under basic conditions, then what happens? Well, I lose the hydrogen, which then means I lose the electrophile. Okay, so neither acidic nor basic conditions. Which is interesting, because what did I just make if I strung that out a whole bunch of times? Say on the order of 80 to 200 times. And I potentially varied what was out here. Change that R to maybe an H, or a CH3, or CH2, CH3, CH3, or a CH2, COOH. Some people have this. Come on. Those are groups. Some people have the answer. You guys just didn't shut it out.
Polypeptide?
It's a polypeptide. It's a protein. So we just said that mechanism is not likely to happen. And yet,
It happens.
it happens. How does it happen? The enzyme does it.
Catalyst.
Yeah. A catalyst is somehow involved that helps increase the activation of, or decrease the activation energy and facilitates that reaction to occur. Okay. This is another big one when we look at our addition reactions. We can encounter what are known as the anionic and cationic chain growth polymerizations. Okay. So when we're looking at our additions, we typically just say we do radicals, but we can initiate those reactions using a cation or an anion. Okay. So in this case, I'm using a superactive, actually sure, name this reagent for me. And as a hint, give me the G name. Could use it as a Grignard reagent, okay, to force that reaction with our alkene, which then makes
Is this like a hangman thing?
yeah, it's a really easy hangman because the answer is already on there. Makes an anion, so we're doing an anionic polymerization or an anionic chain growth polymerization. So we can initiate that either using a really positive structure, a cation, or we can use a very negative anion, and it will kind of propagate itself outwards that way. Okay. Crystalline versus amorphous, just because it's in there. Crystallines tend to be very regular shapes. Okay. Amorphous tends to be less regular shape. Go ahead.
Would that be like your carbon fiber? Would be like the crystal?
So your carbon fiber structures tend to be kind of crystalline, depending on how they're formed and put together. A lot of that comes in with the processing, the post-processing of your material. Okay. If you process it where it's locked into a rigid shape, say flame treat it so that it melts and then freezes in that position, you can maintain a crystalline solid. Other times you have amorphous solids like rubber bands are an amorphous polymer. Okay? And that's actually why they end up being stretchy, due to that amorphous shape. Thermal transitions. Polymers don't officially have melting points because of their very typically irregular structure. So we don't have a melting point, but we do have what's known as a glass transition temperature, okay, which is very, very close to the melting point. Okay? It's the point at which our substance, the individual polymer chains, start interacting very, very weakly with each other. Okay? So it kind of goes soft on you. Okay? And then there were some examples there, but I'm kind of out of time. Spent too much time letting you work on the synthesis. So Thursday will entirely be review. We'll probably start off Thursday with more synthesis. Okay? Maybe make you go back and try and solve that one that I put up on the board last week. And by Thursday, I mean Wednesday. And then it'll be whatever questions you guys have about the exam, which I am in the process of writing.